No. Lesson 2.3 is polynomial functions of a higher degree and modeling. So when we talked back in lesson 2.1, it was the linear function, so x to the first, and it was quadratics, x to the second. This is higher degree, so a lot of x to the third and x to the fourth type stuff. What do they look like? How do we deal with them? What do we know about them? Lots of information about them. So let's jump right in here and get started. As we look at the information, some basic information provided, a polynomial is actually made up of a sum or difference of individual monomial terms. We talked about that when we talked about monomials the other day, didn't we? That it's just the x to some whole number, right? And it's multiple terms added and subtracted. These terms are to be written in standard form. Do you guys remember standard form? Anytime we talk about standard form, you start at your highest power and go down. Probably the most common standard form you guys can think of would be that of a quadratic, ax squared plus bx plus c. But just standard form in general is descending degree. So you start with your highest power and go down from there. We talked about leading coefficient, right? We talked about leading coefficient on a monomial term. Well, when we have a polynomial, leading coefficient is going to be on that first term. So your term with the highest degree. And so we talked about that back in lesson 1, I think, if we jump back 2 lessons there. So leading coefficient will be in front and constant term will be at the end. Okay, so just kind of a reminder, standard form, highest to lowest power. Now, we're going to start with example 1. We're going to look at some graphs here. And these are just official monomial functions. In A, we're going to look at x to the third graph. In B, we're going to look at x to the fourth graph. So I think there's really about 3 things they want us to do here. Describe how to transform the graph of an appropriate monomial function. So we're going to have to use some words here. Of f of x equals x to the n into the graph of the given function. Support your answer graphically, which means we are going to look at the graph. And it also asks us to compute the y-intercept as a check. Okay, so all this information. But let's just look at A and try and break it down. G of x equals 4 times x plus 1 raised to the power of 3. What can you tell me about this graph? What's it look like? What's it do? Anything you can tell me about it? It moves left what? Okay, it moves left 1. A number added or subtracted inside parentheses is going to move your graph left 1. I agree. What else? Go for it.
It doesn't stretch.
Okay. The number multiplying out front is a vertical stretch or compression. In this case, 4 is a number that is much bigger than 1, so it is a stretch by a factor of 4. What is, and I know we don't normally have to talk about this because normally when we do this type of stuff, it's all one type of graph. What type of graph is this? What is the graph that Natalie's telling me to move left 1 and stretch by 4? Y equals x cubed. You see that x raised to the power of 3 in there? Okay. Now, we'll eventually look at the calculator, don't worry. But as we think about this, can you remember, what does y equals x cubed look like? I see some drawing in the air there. It is. It's the one that starts low, it kind of goes up, it kind of zigzags at 0, 0 and goes up. I shouldn't use zigzags. Curves. Okay. On our page of 12 graphs, it's top row, one at the far right. Yes? Okay. So, let me start by writing down the description. Now, when I write down this description, one thing I'm going to comment on, it's not like it's a chapter where they're all quadratics or all parabolas, or it's all absolute value v's, or, there's a variety of graphs. So make sure you tell me what graph we're using here. And so I'm going to talk about, let's see, I'm going to say translate the graph, and I'm going to leave room for a graph over there to my right. So translate the graph of y equals x to the third to the, what do we say, left 1 unit, and we were going to vertically stretch by factor of 4. Okay, there's a description. I put it in words. There's 3 key things I'm looking for in there. Did you state y equals x cubed? Did you state it's a translation to the left 1? And did you state it's a vertical stretch by a factor of 4? Those are the 3 key things I'm looking at. Now, yes, we can look at the graph on the calculator, but I also like to use our brains a little bit to think about the graph. X-axis, y-axis. Okay. The more we think about these graphs by hand, the more you learn about the graph. I don't feel like you learn quite as much with the calculator, although the calculator's good. Okay, as I set up my graph, I counted 2 left and right and 4 up and 4 down. Let's start, actually I'm going to go back to gray here, or black, whatever. What's the graph of y equals x cubed look like? Well, we already talked about what it looks like. Where would be points on the graph y equals x cubed? There'd be a point at 0, 0. Where else? 1, 1. And there'd be a point at -1, -1. Officially, I didn't make my graph tall enough. The next set of points would be at 2, 8. If we just go off of y equals x cubed, 2, 8. Okay, so this is just kind of a sketch of the original graph, right? That's just me trying to get you to visualize the original graph. Now, we talked about the fact that we want to go 1 to the left, which means instead of crossing through 0, 0, I'm now going to cross through -1, 0. Okay. Do you remember how a stretch of 4 works? A vertical stretch of 4, that is. For vertically stretching something by a factor of 4, what does that affect? Our y values, right? It's a vertical stretch. Vertical, when we graph, is our y values. So it was 0, 0. Okay, yeah, we're moving it left 1. But when you take that y value of 0 and you multiply it by 4, does that change? No. Okay. What about it was 1, 1? Okay, my 1, 1 kind of, you can't really see the dot I had there. But 1, 1 was right 1, up 1. So a y value of 1. What happens to a y value of 1? Instead of going right 1 from the origin up 1, we're going to go right 1 and up How many? 4. Because it was 1, 1. Now we're going to go right 1 up 4. Now, my origin is moved, yes. So instead of going from 0, 0, I'm going to go from -1, 0. So from that point, I can go over 1 and up 4. If I had another point from the origin that was left 1, down 1, how does my vertical stretch of 4 make that change? Instead of going left 1, down 1, I'm going to go left 1, down 4, because 1 times 4 again. So in this case, though, when I go left 1, down 4, I end up at -2, -4. Now, as you draw that, you know it's not a straight line, right? Okay. We know it has that curve in the middle. I don't know if I can do this or not. Well, I definitely moved left 1, yes. Can you see a stretch of 4 happening? It's there. It's hard to, a stretch of 4, it's hard to tell there. But notice my graph is a little bit more vertical through the origin or through the center. Now, if you haven't already and you want to graph, grab your calculator and graph. As you grab your calculator and graph, real quick, wait before you graph. What is a quick, easy way? It said to check using or compute your y-intercept as a check. How do I do y-intercept? In order to find the y-intercept, what's my x value? 0, yes? So that check right there would be finding g of 0. So 4 times 0 plus 1 cubed. So 4 times 0 plus 1 is 1. 1 raised to the third is 1 times 1 times 1, which is 1. And 4 times 1 is 4. Is that true? Did my y-intercept end up at 4? Yeah, it did, didn't it? Okay. So right there, y-intercept at 4, it matched. As you look at your graph, one thing I personally think it's helpful to look at. Never should have changed off the. There we go. One thing I think it's helpful to look at is look at the original graph of y equals x cubed. Okay. So if I do y equals x to the third, and then we had, what was it, 4 parentheses x plus 1 raised to the third. If I do a zoom 6, there's x to the third. There's y equals x plus 1 to the third. Okay? So, things to look at, things to consider. Is that something you could do by hand with a little practice there? Did all those pieces make sense? Is that something that's important? Is those pieces making sense there? Okay, unless you have questions, let's go talk about B. H of x equals negative of x minus 2 to the fourth plus 5. I'll put it in words once we talk about all the pieces. What kind of pieces do you see here? Give me one, Natalie.
Moves up 5.
She says it moves up 5. There's a plus 5 at the end. It's not in parentheses, so I could agree with that. Right 2. Yep, I agree, Whitney. Minus 2. Remember, that's left to right. When it's in the parentheses, we're going to go opposite the sign, so right 2. Do you know?
Does it shrink by a factor of 1?
No?
You reflect.
Oh, yeah.
Yeah. When we have a negative, and I mean, officially there is a vertical stretch or vertical shrink by a factor of 1. That just doesn't change anything. So we don't usually mention that. So the negative, though, is a reflection, right? And if it's a negative out front of the entire function, then that is a reflection across the x-axis. If the negative is specifically on the x, then it reflects across the y. Okay? The only thing you guys didn't mention that I want to know, what graph are we talking about? Y equals x to the fourth, right? A quartic graph. Which means here in a moment we're going to have to talk about what y equals x to the fourth looks like, because we haven't talked about that in pre-cal, have we? Okay, so we'll talk about that here in a moment. I talked about that last week and we reviewed it in calc, which is where my brain all, goes together. Okay, so I'm going to say, I'm going to start with reflect the graph of y equals x to the fourth across the, what do we say, x-axis, and translate 2 units right and 5 units up. Okay. I need you to mention the reflect across the x-axis. I need you to mention translate 2 right, translate 5 up, and I need you to mention that it's a y equals x to the fourth graph. I'm going to sketch myself a graph again. Okay. Thoughts on y equals x to the fourth? I don't know if we've ever talked about y equals x to the fourth. Maybe we have, maybe we haven't. I really don't know. So y equals x to the fourth has a lot of different forms. And we're going to talk about those here in a little bit. But the basic yx to the fourth kind of looks like a parabola in a way. Okay? That's y equals x to the fourth. Now, for comparison's sake. Whoops, that's not what I wanted to do. Okay. There's y equals x to the fourth. And then I'm going to put an x squared. So, okay, graphing right now. On the calc, there's y equals x to the fourth. There's y equals x squared. Similar shape, but yet it is different, yes? Okay. Y equals x squared goes out wider, whereas x to the fourth goes up more straight. The other thing I could show you here is if you look, notice how flat that is? That's y equals x to the fourth. It's very flat along the x-axis, whereas y equals x squared is more a quick touch and go to 0, 0. Okay? Gives you a shape, right? So it's still the U shape, but it has more of a flatter bottom. Okay? Flatter base. So, this is, and if you think about it, if you think about some points, it's going to go through 0, 0, right? If we're just looking at the basic. It would also go through 1, 1, right? Because 1 times 1 times 1 times 1. Negative 1, 1. When we get to 2 to the fourth, that'd be 2, 16. I'm not going to do that. But, so your basic quartic looks something like that. Okay? In other words, that's part of the reason it goes up straighter is because it's going up headed to 216 instead of 2, 8 next. Now, we got to take this graph and alter it, right? Can you visualize this here? So right now it's a right side up U shape or quartic graph. What do I do with it? That's going to reflect, so it's going to be upside down, just like a parabola, right? That vertex, it was at 0, 0. Where's that vertex going to go? 2 right and 5 up. You know what? I know when I was counting, I only counted 4 up on when I was, putting the tick marks on. So what I would do is, kind of like when we graphed parabolas and translations, I'm going to take my vertex, I'm going to count 2 right, 5 up. Okay. We don't have any stretch or shrink. So think about what your basic quartic did. From the origin of 0, 0, it went what? 1 over, 1 up, right? Well, now, where am I going to go? Instead of 1 over, 1 up, I'm going to have to go 1 over and 1 down. Except I will say, I don't like where my dot ended up. There we go. So I'm going to go 1 over, 1 down, 1 over, 1 down. And I'm going 1 over, 1 down because I'm reflected upside down, yes? So that is my recommendation of an easy way to draw this, or easy-ish way. Looks something like that. Not perfect by any means on my behalf. Now, we're supposed to compute the y-intercept as a check. I don't even have mine crossing the y-axis yet. However, it can still give me an indicator if it's right or something. Because if I get a y-intercept that's up above my quartic, then I know I have an issue, don't I? So if we plug in 0 and check it, h of 0, negative of 0 minus 2 raised to the 4th plus 5. Well, 0 minus 2 is negative 2. Negative 2 raised to the 4th. What's 2 of any power rate, or 2 of any type raised to the 4th? 2 to the 4th is 16. A negative 2 to the 4th is still 16. But what's this negative say? We're going to make it negative again. So it's negative 16 plus 5, which is negative 11. Could a y-intercept of negative 11 make sense? It's going to be down here somewhere. Could my graph end up over there? Yes, it could. If I'd gotten a y-intercept right here, up here somewhere, that would make sense. But the fact that we were going to have to go 2 over and then 16 down, negative 11 makes perfect sense. Okay. And did you graph it on the calculator if you wanted to? I showed you the original, so I don't know that I need to go graph this one on the calculator. Really? We're down to that little time already? Thought I had a little bit more time than that.
I went to x equals 0 and it's y equals negative
Okay.
11.
Okay, so checking the y-intercept on the calculator. Good deal. Okay, so example 2, I got a couple minutes, but I don't have very long here. So we could just kind of start to talk about example 2, and we'll have to talk more about it tomorrow, obviously. We get to example 2. They want us to graph this polynomial function. Okay, so we're going to be asked to graph f of x equals x cubed plus x. We're going to talk about locating its extremas and zeros, and explain how it's related to the monomials from which it is built. Okay, let me take a vocabulary moment. It wants me to locate its extremas. Okay, so remember, in pre-cal, when you're asked about the extremas of something, you are being asked to find the mins and maxes. And we have a handy dandy calculator that can help us out there, right? Which we'll need to. And then it also asks us to find the zeros. What's that vocabulary word mean? Yep. So zeros, we're going to be talking about x-intercepts. Okay. And then we'll talk, when it talks about how is it related to monomial from which it's built, the question is going to be how is it related to the x cubed that's part of the equation and the x that's part of the equation. Okay? So tomorrow we will start there. So when I'm taking attendance, I may have you guys go ahead and graph that and start considering extremas and zeros and what the shape of this graph looks like. Okay? No homework due tomorrow. This homework right here that's up on the screen, there's another section that adds to it that I didn't even write up there, but I forget. Does this go with front and back of this page, maybe? I feel like that's what it is. Okay?